Hi guys, today we are going to be learning about Laplace transforms. Before we start, I would like to talk about the application of Laplace transforms so that we can develop a little bit of interest. So Laplace transforms are used in solving differential equations, for example, and they are also used in analyzing systems in engineering and physics, such as electrical circuits, control systems, just to mention a few here. Of course, some of this information is available, and you can look it up on Google. So, before we define what Laplace transforms are, I would like to talk about a way in which we can think about Laplace transforms. So we know the importance of Laplace transforms. So it's important to have a mental framework of how they fundamentally work. So a Laplace transform, as the name suggests, transforms a function, for example f of t, by doing something into another function uh, which we can work with in the things that we are trying to do. For example, we said that we can use Laplace transforms in solving differential equations. So a Laplace transform is basically like a machine that takes in a function as an input. Remember, the difference between a function and a Laplace transform is that a function takes in a variable. For example, the function f of t takes in a variable t, but a Laplace transform takes in a function as its input and operates on that function to give out another function which is in a desired form. So a Laplace transform is just an operator in a nutshell. Then with that in mind, we can define the Laplace transform as follows. So the Laplace transform of a function f of t is defined by the integral. So the integral of the function, which is the input f of t, multiplied by the number e to the power negative s times the variable t, which is the same as the function here. And of course, we are integrating between infinity and 0, and we are integrating with respect to t. So yeah, so you just basically get the function. You get the function f of t, and you plug it into this thing, this integral. Then you have your Laplace transform. So that's how you define it. That's how it looks, and yeah, that's how it's done. So we can also talk about the notation that is commonly used when you are working with Laplace transforms. So all these are the notations that can be used to 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 show that a Laplace transform is being applied on a function f of t. So you can use this notation, you can use this notation, you can use this notation, and this notation can be used, all these notations can be used, and I might use these notations interchangeably as we move on, depending on which one is more neater and cleaner, if there is such a thing. English is not my first language, so you guys will bear with me. So we have we have established that a Laplace transform can be defined in this manner, and it can also be uh, notified in this way. So we can put this together to say we are performing a Laplace transform on a function f of t, and this is what is happening basically. So it's just showing the things that are being done to f of t for us to get its Laplace transform. So a Laplace transform has some linearity properties, which we can discuss here. So we are looking at the linearity properties of a Laplace transform. So the Laplace transform, as we've discussed, is basically an integral, and we know that an integral, when we have a function being multiplied by a constant and then we are integrating, we can basically push the constant out of the integral. So the same applies with the with the Laplace transform here. In this notation, we see that we have k here as a constant, and we have the Laplace transform of the function t, but the function t is being multiplied by a constant k. So what we are doing is we are basically pushing the constant out of the we are pushing it outside of the Laplace transform, and then we are just finding the Laplace transform of the function f of t, and then we simply multiply with k at the end of the day. So if you have this, you can simply push the k outside, and you have outside of the Laplace transform, and you have that at the end of the day. So again, there's another there's this property also. You can distribute the Laplace transform if you have two functions that if you are applying the Laplace transform on two functions that being added or subtracted together, you can basically distribute the Laplace transform just as we do in algebra. We can distribute the Laplace transform as shown. So yeah, the Laplace transform is therefore termed as a linear operator because of these two properties. Yeah, so then we can also talk about the Laplace transforms of elementary functions, which I will talk about in the next video. So yeah, thanks for watching. See you in the next one.